All right. Oh, thanks. Oh, sounds good. Okay, so again, this is, what's the name of this problem? The calculusy question, right? And so you've got this particle, it's a distance away from this uniform rod, and we're trying to find the force of attraction between the two things. All right, what I think I didn't do a great job presenting in the notes is that this equation is, technically speaking, it's the equation that you use to calculate the gravitational force of attraction between two point particles. Okay? Now, if you've got two spherical objects with no overlap, it still works because you can treat the objects as being at the center of mass of the two spheres, and then the distance is the distance between those centers of mass. Okay? But technically speaking, this is the equation that you would use to calculate the force of gravitational attraction between two point particles. So surprisingly, what doesn't work is what you can't do here is you can't just find the center of mass of the rod and then find the force of attraction between the two. Okay? It works with spheres, not with a rod. Okay? And the reason for that is complicated. Basically, it's because of this r squared. This mass out here is going to have a significantly less gravitational force of attraction out here than you would have with one closer, right? You know what I mean? Like if you looked at like a, one molecule here and one molecule here, even though this one is sort of like twice as far away, it doesn't mean it's going to have half the force because of the d squared thing. Okay? Did that make a little bit of sense? Yeah. All right. The why it works with a sphere is a little bit more complicated, and that's what that video that I posted on Schoology the other day was about. Here's a super quick explanation of why it works with a sphere for the like two of you that care. All right, so here's two objects. So the idea is, oh shoot. Yeah, kind of. I mean, the idea is these points are farther away, but there's also less of them. I don't know. That's kind of a half-assed explanation. I guess at this point, let's just remember that it works for spheres. If it's not a sphere, then you got to calculus it. All right? So here's what we're going to do. We're going to treat this thing as a whole bunch of point particles. Okay? So to break it down into point particles, we need to break it down into a whole bunch of tiny little particles of mass dm. Okay? And then we're going to sum up all of them. Follow? So that makes me think, oh, I'm going to take an infinite sum, right? In other words, an integral. Okay? So what I want is, this is how I sort of processed it conceptually, is that the force of gravity between these two things is going to be the sum of g times m1 times little chunks of mass over the distance to them squared. Follow? Yes?
So would that be d capital M?
No. We're finding the force of attraction. Oh, gotcha. So what does dm represent? That's what I haven't explained. Yeah. Sorry. So little dm would be like some little chunk right here. So if you sum up all of your little dm's, it's going to give you capital M. Does that make sense?
Yeah.
Very good question. Everybody good? All right. So we want to write this then as an integral. So our force of gravity is actually the integral of g times m1 times dm over r squared. All right, and our mass, right now we're integrating with respect to mass, right? So we need to integrate from 0 mass until we get to the total mass. So that's a capital M there. All right, did I lose anybody there? So this is, I don't know how to say this. This is the first time when you've sort of been expected to use calculus, but I haven't sort of flat out on the front end given you the equation. You know what I mean? So this is more about problem solving than anything. All right. So is everybody good up here? Okay. So now our problem is this is little m1. That's not the same as this little m over here. Okay, which is another good reason why I left it as m1 over here. Okay, that's probably why they did that, actually. All right, so we want to integrate with respect to radius, so we need to do a change of variables, right? So this is that same linear density trick that we did before, right? Anybody see where we're going to go? Somebody give me a hand. What do we got? Thomas? Yeah, exactly. If you didn't hear him, because he was very quiet there, he said the mass of the whole rod divided by the length of the whole rod. Because the rod is uniform, that's equivalent to the mass of any little chunk divided by the length of any little chunk. And so multiply, and you get that dm is m over L dr. Whoa, why does it keep doing that? It's so weird. My smartboard is possessed.
Was there a scenario where you have to do it for a non-conform?
No, yeah, honestly, this is the only such problem that they could give you without the calculus just getting bonkers. So like, if you know how to do this one problem, that's it. All right, so is everybody good up to here? All right, so let's go down here and make our substitution. So I'm picking up here with the blue. So the next line there becomes, well, our force of gravity is now the integral of g times m1, m1 being the mass of this little particle over here, over r squared, right? And then I'm going to replace dm, with this. So m over L dr. Any problems? All right, now what are my bounds of integration? Do I still go from 0 to m? So I need to go from the distance where I first begin acquiring mass until the distance at which I've acquired all of the mass. So my lower bound is 0.23, and my upper bound is 3.23. Does that make sense? Because there's no mass in those first 23 centimeters. Follow? Any problems? Okay, so from here, I'm going to say, and you're all going to groan at me, it's simple calculus. Thank you for groaning. Okay, so let's see. Let's pull out the constants. So what's the only thing here that's not a constant? The r, right? So let's pull everything else out. Fg is g times m1 times capital M over L times the integral from 0.23 to 3.23 of, it's 1 over r squared. Let's write that as r to the negative 2. All right. Any problems up to there? We are almost done. Any questions? Okay, so what do you have to take the derivative of to get r to the negative 2? So remember, when you take a derivative, your exponent gets smaller by 1, right? So it must be negative 3 or negative 1, right? So this is going to be r to the negative 1. If I take the derivative of that, that would give me negative r to the negative 2. So I got to tack on a negative sign, right? So it looks like I've got that. And then I want to evaluate it between 0.23 and 3.23, and then times this whole constant mess over here. Cool? So you end up getting g m1 times m over L times, let's see. So r to the negative 1 is just 1 over it, right? And you always want to do top number minus bottom number, right? So it's negative 1 over 3.23 minus negative 1 over 0.23. And then plug in your numbers and solve it. Yes.
So we have to show the intent or could we just plug in our calculator?
So if you know how to take an integral on your calculator, I've been told that's acceptable, which is,
Less cool.
I agree, yeah, but it is what it is.
Yeah,
All right.
but it makes you lame. It's all about style.
Everybody good? Does this make a little bit of sense? Some? Okay. All right then. I think that's it for that one. Questions with it? All right. Let's see. Where's my recording thing? We'll stop recording.